I'm Paul Nygaard with ICS Group, as Kate indicated. I am the president of the organization, and we're going to talk a little bit about here what I feel is an important topic. As engineers, I'm an engineer myself. I'm a graduate of Michigan Tech University, civil environmental. I've been in the industry going on 30 years now, and we as consulting engineers and us as manufacturers rep, we have to do everything we can to help our customers, either industrial or municipal, to try and meet the challenges that they're facing right now. And what we'll talk about today are some of those challenges that they could typically face that we see primarily when we're out talking with our customers and our engineers. What are the typical problems that we see them challenged by? And there's multiple different facets of those challenges, not only technologically, but also on other basis or other points of discussion. So what I'll do here to save a little bit of bandwidth in the presentation, if that's an old term or not, I'll turn my camera off here. But as we go through the presentation, if there's anything that triggers in your mind, questions or anything like that, feel free to interrupt me, and we can kind of take a dive into any questions you have here as we kind of move through the presentation. I'll be mindful of time here because I know for you guys, time is important, and we'll try to keep this under an hour here as we go through it, and hopefully we'll have a little bit of time also at the end to do any kind of question and answers. So I will go ahead and share my screen here. As I get this window to pop up, there we go. Kate, you want to confirm when you see that?
Yep. You
Okay.
just need to hit Control L.
Control L. I click in the window, it'll help. There we go. That should have probably made it full screen, right? Okay.
Yep,
so
you're good to go.
All right, good. So as I mentioned, what we're going to try to attack here today as topic points are the pain areas or issues that we see a lot of these plants and operators having to deal with. So when we get into looking at wastewater in general overall and the current plants that are out in the Midwest and across the country, quite frankly, most of these plants, at least in the versions they are right now, were developed when the Clean Water Act was passed back in the early 70s. Most of the mechanical and municipal wastewater treatment plants that we all typically run into and work with on a daily basis were built around that time. So they're approaching 50 plus years old now. Granted, a lot of plants have gone through a number of different upgrades or enhancements over that course of time. So we have aging infrastructure really that's starting to impact a lot of these plants, and most equipment that is put into plants, usually we target somewhere between a 15 and a 20-year life cycle. So every time you go through an upgrade, you kind of reset the clock on that piece of equipment and it moves the clock forward. So from that standpoint, that's one of the big challenges, is always trying to keep the plant up to date, do the maintenance, things like that. On typical average, the typical municipal wastewater treatment plant is somewhere about most 81% of them are somewhere at or near design capacity. There's a handful or 15% of the population of the plants out in the market that have exceeded capacity. So that's a big challenge, and that's going to get worse as we go along because of changing demographics, such as changing populations, where some municipalities will experience a reduction in growth, some will stay stagnant, and some will increase in growth. And all of that has an impact on the amount of flow coming in and out of the plant and whether or not it's able to achieve its capacity requirements and its treatment requirements. Wastewater characteristics is a big one. Basically, the question is, what's going on out there? There's a lot of stuff that's changing in the demographic of or the type of makeup that we're dealing with in wastewater. This isn't your typical domestic wastewater anymore. There's a lot of emerging chemicals of concern. Microplastics, you've got PFAS and PFOA is a big target right now that a lot of municipalities are dealing with, not only in the wastewater side, but also in the drinking water side. There's more and more higher industrial loads that are coming into plants. So for instance, in Wisconsin, we have a strong presence of industrial manufacturers such as food plants, beverage, yogurt, cheese, meat facilities, things like that, that discharge to municipal wastewater treatment plants. In those heavy industrial high strength loads can have a significant impact not only on the biological loading coming into a plant, but also on the fluctuation in flow, which can obviously cause a lot of challenges. Also, water conservation is a big one that we're starting to see more and more of. Not so much here in the Midwest, but for instance, out on the West Coast, we hear a lot of people talking about they're in such drought conditions that this starts to affect wastewater treatment plants, that they put conservation efforts in place, which then reduces the amount of volume in, which means the volume that's coming in obviously is lower, but now it's more highly concentrated, which can have a big impact in the operation biologically of a wastewater treatment plant. Other things that can be challenging are obviously state and federal funding. Is the funding going to be enough to do a project or to do an expansion? And then, of course, staffing shortages. We can kind of get a pulse right now that there's a lot of older operators or older people running these plants in the industry that are starting to age out. They're getting to the point where they're going to start considering retirement or moving into retirement. So who's going to replace them? When a lead operator retires and they can't fill that spot, well, then they're left with one extra or one less guy. That means they're trying to do more with less people. So that's a big challenge. And so one of the big questions is how do facilities manage more with these limited budgets and challenges and resources? We're going to talk about that a little bit. Is there a way to do more with your existing infrastructure? Do we have to go into a full-blown plant upgrade, expansion, or something along that line where we're adding physical footprint in physical tankage and increasing capacity that way? Or is there something that we can do to improve or just simply replace equipment that can help solve some of these problems? So when we talk about the major issues in a plant, obviously CapEx and OpEx, that's the big one. How much money do we have to spend for an upgrade? What's it going to cost? Is it going to impact and drive our operating costs up, or are we going to have the ability to improve overall plant efficiency with the use of the technology? A lot of the things that we're going to show you here, and I'll preface before we get into the discussion, what you'll see here from us is we're going to specifically focus on the areas of collection systems, primary treatment, secondary treatment, and biosolids management, which are inherently usually the big problem spots and challenges for these operators in these facilities. You'll see a lot of technology that we have to offer in the marketplace that can help address those issues without significantly impacting manpower and capital budget. And in most circumstances, if not all, will have the ability to help them reduce their operating costs and improve their operations overall. So that doesn't necessarily mean that our solution is the only solution, but the discussions today will kind of highlight what we can all be looking for as far as technology that might be something a little bit more easy to enter into the plant than doing something like a full-blown upgrade. So when we talk, we'll get right into collection systems, and the way we kind of structured the presentation here is to start at obviously the collection system, which is where all of our wastewater is getting collected, and then we'll funnel that into the plant and then out the backside of the plant with the discussion points here. So when we get into collection systems, obviously the challenges that are out there in that network are primarily related to the lift stations and mechanical equipment associated with the lift stations. So we usually end up in a situation where you can get a lift station where plugging and ragging has become a big problem. A lot of use of sanitary wipes and things along that line that cause significant issues where once you get a rag or a ball that starts to form inside of a volute of a pump, if that thing doesn't get mitigated right away, it's going to cause imbalances, mechanical disruption, and it'll plug the pump. Then the operator's got a challenge he's got to go out there and deal with. Some of the other things in the collection system, FOG is a big one, where you get fatbergs and fat layers that start to develop on top of a lift station, especially a lift station that maybe has lower flow rates than a high capacity lift station. When you get that material that sits in there for a while, obviously it's going to start dealing with sepsicity issues. The FOG will be a big thing that will cause, and you get that biological component in there where you've got a lot of BOD and solids in that lift station. You'll end up in a situation where you get stagnation and then things start to go anoxic and then finally anaerobic, and you start to get a lot of H2S where you get all those adjoining property owners maybe that are complaining about odor control and odor issues coming from a lift station. That H2S will cause corrosion of the internal piping and components within that lift station. All of those things, when they eventually start to happen, also generate employee hazards. You can imagine if an operator, and we've seen some horrific pictures of pumping systems and mixers and things like that that go get pulled out when they have a plugging problem, and the operator's got to tear that thing apart, and they end up with this big ball of material. There's all sorts of hazardous material in there. There could be syringes and drug paraphernalia. There's condoms. There's all sorts of things that are all in that ball, and obviously that creates a hazard. The H2S gas can be a hazard also from an asphyxiation standpoint. So traditional solutions that normally people will look at will be something along the lines of, for instance, a vertical screen that they'll mount on the end of the pipe to be able to take some of that inorganic, stringy, plugging type material and bring it to the surface. People will look at grinders and put grinders in on the end of the pipe before it goes into the lift station. Or they'll actually go in and retrofit their pumps out to something that's more of a non-clog, a grinder, or something along that line. All of those solutions can be fairly invasive and capital intensive because you're going to potentially have to do structural work and controls work and electrical work and things along that line. And again, that goes back to the challenge of, do we have the budget to solve the problem? And those are some of the things that can potentially happen there. So one of the technologies that we have that can be really straightforward and very quick to deploy and also very quick to solve the problem in CapEx light, where it's cost effective, is our product called Deragger. And you can see in the picture here what this is basically it's a control module that would get mounted inside the control panel on the DIN rail. And that thing would then be hooked up. It gets powered right from the control panel. We have CTs that we mount on the power leads that go down to the pumps. And what that thing is doing is what we call real-time pump monitoring. So it's looking at voltage and amperage of that pumping system, and it'll start to map the power usage curve. So the first thing we do is we make sure the pump is clean. That thing goes online and gets commissioned, and then it starts to monitor what's going on inside that lift station with the pump itself. And as it starts to see an increase in amperage and a reduction in voltage, it will put that pump into a reverse cycle and kick that blockage out, effectively eliminating the potential for the blockage to even start. So it also has the ability to monitor unbalanced load, so it can sense if the impeller's out of imbalance. It can sense if we're having bearing issues within that lift station, which will allow the operator to more effectively manage the lift station before something becomes a problem. The key being that trying to keep that volute and that impeller clear at all times of material is vitally important, because that can significantly reduce the amount of maintenance and cost associated with dealing with the lift station. So some of the benefits of this simple technology in comparison to the other ones I talked about, which are intensive and invasive, both from a manpower standpoint and also a cost standpoint. This eliminates downtime and other costs associated with pump ragging. I mean, it basically is going to eliminate the problem, which obviously, if you eliminate the problem, you're going to reduce the safety risk to the operators, and that's a big deal. These guys are not having to go down in these lift stations, or they're not having to pull pumps up to the surface to deal with these issues. We have the ability to put a cycle in where we can program this thing to do a purge of the lift station. What that in essence means is we can get it to cycle the lift station, turn the pumps on, and draw the lift station completely down. So if you've got an FOG layer that's starting to form, let's say you do that once a day, you're going to eliminate that FOG layer. If you're getting the FOG layer out of there, you're going to end up taking away the ability of anoxic or anaerobic environments to start to develop. And you're going to significantly reduce the H2S generation potential of that lift station, and in essence, reduce the odor being generated from it. The obvious thing on the mechanical side is it's going to significantly reduce lift station failures. The technology, like I said earlier, is simple plug and play. All we need is one-line diagrams and information on the pumps, and this is usually a one-day retrofit. It can also have the ability, because we are going to be closely monitoring power usage and reducing excessive loads, we see sometimes up to 40% reduction in energy usage. So that goes back to helping the operator reduce their operating expenses. Typical payback on this thing is usually in the range of less than a year. So you can compare that to, for instance, a fine screen that might cost $150,000 to install. We can get into a duplex lift station for around 15,000 bucks and solve the problem in the same way. But then they're not having to deal with mechanical pieces of equipment that are in addition to the lift station itself. So some really significant benefits there that can help these operators manage things out in the collection system more efficiently. So then once we get out of the collection system, obviously, we're going to get into pre-treatment, specifically primary treatment. So this goes back to the issues of plant capacity. Plants, again, getting closer and closer to plant capacity. So traditionally, how do you deal with plant capacity? You go in and you look at increasing tank volumes and increasing physical footprint of the facility to be able to handle more load and more hydraulics. Plants can be challenged that way because of limited footprint. Wisconsin's a little bit more forgiving because a lot of these plants have, fairly good access to surrounding land, but nonetheless, there are a lot of challenges even trying to get that permitted and get the availability of land to be able to expand the plant. Another big one, obviously, is changing influent characteristics. As I said early on, one of the big challenges that we're seeing right now is this is not your typical domestic wastewater anymore. You're ending up with a lot of weird chemicals and additional surfactant loadings. One of the big things with surfactants was during the course of COVID, obviously, people started using a lot more soaps and a lot more disinfection products. That has created significant problems in wastewater treatment plants because they're dealing with surfactants. And then, of course, you've got your industrial loads, especially from food production, where we get FOG loadings and things like that, which in essence is also a type of surfactant. So one of the things that we have is a technology that can help deal with that. Simple to deploy. We can pilot these things on site, and it treats the entire wastewater treatment process. Is a technology called Moliere, which is a nanobubble generator system. This is a really unique technology that has well-proven significant benefits in the wastewater treatment process. There's over 2,000 projects installed across multiple different areas: agriculture, aquaculture, wastewater, surface water, oil and gas. And what these nanobubbles do is they have the impact on, there's a number of key impacts, but most importantly, it improves the efficiency of the overall wastewater treatment process by increasing the ability of the biology to go to work and basically break down the waste constituents more efficiently. So there's a lot of key benefits to this that we'll talk about here. We'll talk first of all about how it works in general. This technology, because the nanobubbles are extremely small in size, as you can see noted here, they're about 100 nanometers in diameter. So we're talking about stuff that's viral cell size, very, very basically non-detectable by the human eye. Those bubbles, when they have a very high electrochemically active surface, and they have high internal pressure. So they have no buoyancy. So it's a Brownian thing where they carry, once they're injected into the wastewater, they carry through the wastewater column. So it's not like a dissolved air flotation system that the air bubble gets injected and then it latches onto a piece of material and then floats it to the surface. These bubbles stay in suspension throughout the entire process, from the front of the plant back through the secondary treatment process. So what happens is that the surfactants and FOG and all these different chemicals attach to those bubbles. And what eventually happens is the weight of that material collapses the bubble. And when that bubble collapses, it releases a tremendous amount of energy, which then disrupts the the actual molecular makeup of these different chemicals, such as FOG and surfactants, breaking them down and making them more readily degradable from the biological standpoint. So that in principle is what it basically looks like. And this picture here is a typical small system. We have the ability to pilot up to, I believe, 5,000 gallons a minute. Where this is usually applied is at the front end of the plant. So we're going to be looking to apply this technology where you have a headworks facility, and typically right after headworks screening and grit removal. Once we get past there, we usually deploy it right before primary clarification, because then it has the best ability to get into the plant and really start doing what it's going to do. Some of the benefits that have been realized, and these are well-documented white paper type stuff, independent studies. We've seen reduction in surfactants of 35 to 55%. We get a really big impact on TSS enhancement in the primary clarification and secondary clarification step, where we'll see TSS removals of 10 to 25%. And we'll get 90% settling of sludge in less than 2 minutes in an Imhoff cone, which you can imagine now is going to have a big impact on how that primary clarifier system is running at a plant. And once we get the solids out of the way, now your secondary aeration process can operate more efficiently. And what we see there is a significant impact on the ability of the plant operator to reduce we realize an increase in oxygen transfer efficiency, which then allows the operator to lower their DO set point. One of the case studies we have, they actually were able to turn down their DO set point from 3.2 to 2.5, which resulted in a significant reduction in actually them being able to turn off one of their blowers. So that had a big impact, going back to one of the key things we're trying to help with here in reducing energy consumption. So that's one of the big impacts of the technology. Other things we've seen come out of the technology is it'll actually help improve sludge thickening and dewatering. That same application that I just referenced, they saw an increase in their dewatered cake from 12% solids to 17% solids. That's because you're getting that surfactant out of the way and converting it to a biological solid instead of that greasy, soapy material going through the system and ending up coating all the biosolids presses and things like that. And it also has an impact on reducing chemical usage, because if that stuff is more readily dewaterable, you'll have a reduction in polymer consumption. And other things, we've seen a significant reduction in foaming in basins, reduction in odor output from clarifiers in activated sludge basins, and it prevents sludges from going septic. So again, this is a simple deployment that can be installed typically in a day or two at the front end of the plant. And then usually within 30 days, they can really see the results of that technology taking effect within the entire operation of the plant. Another thing that we can look at when we start talking about footprint characteristics, let's say, for instance, we have a plant that has a capacity issue and they're looking at, we need to deal with this. We've got increased load, both hydraulically and biologically. They will look at, okay, we have to expand, add more tanks, add more clarifiers, add more aeration trains, or is there another way we can really deal with that or repurpose those tanks? And that is where the Nueva Energia prime screen comes into impact or comes into play here. That particular technology is a primary treatment step. It literally can take the place of your primary clarifiers. So just imagine you had a plant that had 200-foot diameter primary clarifiers, and their capacity issue is they're starting to look at having to expand the plant. They'll look at, okay, we got to add another clarifier, or we have to add 2 clarifiers, or you can drop this thing in front of the clarifier, and it can take the place of the clarifier. And then you can repurpose those clarifiers for potentially, let's say, equalization, Or one of the technologies we'll talk about a little bit further down here is, can you convert that to an aerobic basin and use that capacity then to increase your aerobic capacity, if that's part of what the design expansion is going to have to be. So this is there's over 2,000 of these filters in operation since the 1980s. You can see they're an all stainless construction, including the disc. So when this material gets captured, your solids that typically would be, for instance, when you look at a primary clarifier, you're going to slurry primary solids out of there and waste them either to biosolids processing or anaerobic digestion or some other process step. These solids come out the back or the side of this unit at somewhere between 6 to 12% dry solids range. And that could be slurried directly over to a digester without the need of any kind of primary treatment or any kind of thickening. So there could be a savings in a process step there because they're already fairly concentrated. So I'm gonna actually switch gears here real quick, and I'm going to share another screen to kind of give you a video. It's like a 1 or 2 minute video here that'll show this screen in operation. So just bear with me here for a second. Bounce over here. And we'll turn that on. I apologize. I grabbed the wrong one. I jumped to the wrong screen. Get this right here. Bear with me. It is not grabbing the right video. I apologize for that. Let me just refresh here. There we go. Now we got it.
Can you explain to us what's going on in the video, Paul?
What's that?
Can you explain what's going on in the video?
Yeah, so what you see here is this is primary solids after headworks. And what you see happening here is this is I'll pause this real quick if I can get to it. So this is your head box of where your raw wastewater is coming into the head box of the unit. And then I'll go back over here. We'll just replay this real quick so I can walk you through it with the pause button. So these discs, the flow is going between the two discs, and what the discs do, they're a stainless steel mesh that uses what we call cross-flow filtration. And you can see once we get in between here, that's what it's primarily doing, is these are the solids that would normally be captured by a primary clarifier. And again, that's your influent level control there on the right. And then these are your primary solids that are being captured by that. And then that can be slurried over to the anaerobic digester. All the maintenance is above the water line, which again goes to helping the operator reduce their operating expenses and issues associated with maintaining a system. So that is in essence what the prime screen does. So we will go over here and I'll turn my screen back on to our presentation. So net impact of that technology, it literally can eliminate the need for primary clarifiers. Or if you have primary clarifiers, like we talked about, if you're looking to expand the primary clarifiers, you may not need to because we can replace the primary clarifiers with this technology. Again, so they can be repurposed and used for other things such as equalization or additional aeration. We typically see 50 to 70% TSS removal, 20 to 40% BOD removal. Again, the slurries can be sent right over to an anaerobic digester. The interesting thing that I forgot to note in this presentation when Kate and I created it, this is literally 90% smaller in footprint than a primary clarifier. So our smallest unit that can sit in a footprint that's about 8 feet wide by 16 feet long can do 3 to 4 MGD through it. So you can imagine how aggressive you can get here for an operator in helping them enhance their plant operations and repurpose things and really get aggressive with treatment design and helping them deal with existing infrastructure and helping. Yeah, so there's a question here from Rebecca. There's a couple of questions I saw just flash up here in the chat. So yes, so if you look at this, the flow comes in between the discs and then it flows out into this chamber where it sits in this barrel, and then the water flows out into this tank, and this is your discharge out the bottom of the tank. Then the solids get walked up by, so this is rotating in this picture here in a clockwise manner, that those solids basically start to snowball in there. And once they snowball, they walk themselves up to this discharge chute, and then you can slurry that away. You can either take it to a biosolids process like a thickener or additional dewatering, or you could take it to an anaerobic digester. Hopefully that answered the question for you, Rebecca. So one other question she had also was, what is the size of these units? This one right here can probably do right around an MGD. So there's 4 discs on here. That can do probably an MGD. They have systems that are in 150 to 200 MGD plants right now. So they can make these systems extremely small or really, really large. And that's just a functionality of adding discs, really, because there's a hydraulic loading rate feature of this. We're getting typically somewhere around 200 to 250 micron mesh on these discs, and that's what is the equivalent of giving us the removal efficiencies that you see here that are what we try to obviously focus on is being at or above what 10 state standards say for a primary clarifier or primary treatment design requirements. So again, the benefits of that technology is it's high efficiency primary treatment. We can literally drop these into existing structures and channels. So we can either do them in an in-channel structure or we can pump to them. So either way, we can do them either by gravity or by force flow. They're extremely small footprint, but yet completely scalable up to whatever size we need to accomplish. Again, going into the hundreds of millions of gallons on a system, and they're extremely easy maintenance. The water level is always above this shaft point here. So the operator can maintain these discs above the water line. He never has to drain the tanks out, never has to do any mechanical equipment repair or anything below the water line. Again, going back to one of the themes of our discussion here, how can we help these guys do more with less? One of the other things, obviously, with secondary treatment issues with expansion and the challenges is aeration. Traditional aeration, we got fixed grids on the bottom of a tank with typically 9-inch fine bubble diffusers, flexible membrane diffusers. The big issue that comes out of that is those types of things wear out over time. And the operator then to be able to do maintenance on it, what's the first thing he has to do? He's got to drain the plant down. He's got to go into that tank and either muck out grit that potentially could settle out, biological stuff that could settle out, and then they're offline from a maintenance standpoint. So that's a big deal. Because that takes a lot of effort. And then they got to get that material out off the bottom. They got to go down and repair discs and cracked pipes and things like that. These issues become more prevalent when you have existing plant capacity where you're getting maximized out again. How are we going to add more aeration capacity when you have a limited footprint and we can't start looking at basins? Changing influent characteristics can drive up the requirement for dissolved oxygen and more air into the system, which is going to, again, drive up operational costs such as energy and things like that. Like I just highlighted, below water maintenance is a real big one. How do you visually inspect it to even know something's going on? Well, the way you start seeing it is you can visually see from the surface, there's an area where maybe they have some diffusers out and things like that. Grit and inorganic deposition and energy costs. I mean, aeration, in essence, is the biggest energy consuming point in a wastewater treatment plant. Quite frankly, when we talk about just going back to the discussion about surfactants, 40 to 60% of energy usage in a dissolved oxygen aeration basin, like an activated sludge process, can be attributed to the detrimental impacts of surfactants alone on oxygen transfer. So just imagine you get that surfactant out of the way, you're going to get somewhere in that ballpark of a 50% energy reduction. Then you couple it with this technology here that we have. This is kind of an advancement now of traditional fine bubble diffusers. This is a company that we work with called Jaeger Aeration, and they manufacture oxy-strip diffusers, which you can see on the side here are longer diffusers. They're not tubes; they're more oblong or oval in shape. They're flat, and there's a huge efficiency gain from that. So by deploying those types of diffusers, we can help the operator reduce his operating expense related to energy usage by somewhere between 20 and 40% just by more efficient distribution of dissolved oxygen within the reactor itself. These things can be made from EPDM, silicone, polyurethane. Expected life is 10 years, which helps obviously with maintenance. Give you an example of the efficiency gains here. One of those pink strips here is the equivalent of nine-inch disc diffusers. So there is a large reduction in the amount of diffusers down in a basin, which is a big deal. And I'll show you some pictures here where we start looking at, and I'm sure you guys have seen these basins open when they have all these diffusers. It can be mind-boggling at the number of diffusers that have to be maintained down there. So that's a big deal. And then just imagine when they start getting deposition of materials down there and they start to bury those pipes and they start to bury those diffusers, and then they have to go in and clean that. They got to work all around those mechanical components. It's really labor intensive. So then what we do is we couple those diffusers with a design called the OxyLift design. In one of these frames that you see here, is the equivalent of 162 9-inch diffusers. So you can imagine in that small footprint how much oxygen in mixing energy we're putting into that basin in a much more compact footprint. The unique thing about this is it's a completely retrievable system. So all that stuff I just talked about with traditional diffusers goes away. We can eliminate for the operator ever having to pull the basin down, take out dirt and debris, and have to deal with maintaining something below the water line that he's got to go and deal with in the tank. And this particular technology is not limited by the tank geometry. So what I'm going to do here is I'll turn off my screen again. Then I'm going to show you a couple videos of this particular technology in action. So this is a circular reactor aeration basin. We can do these again in any geometry, and I'll show you some other examples. But this is a bridge-mounted system. We'll make this bigger here. So you can see what's going on here. They just turned the air on. I'll stop this real quick here. So this is very similar to a submersible pump system in a lift station on a rail. So these racks are down below, and you can pull these up to the surface on a rail system. And that's where we get that feature of not having anything in the tank that needs to be maintained. So what we have on these piers out here are basically mixers that are basically getting a flow counter or clockwise. You can see the flow in the tank where we're getting mixing in the tank. So we're decoupling the mixing energy from the aeration energy, which has a big impact also on energy efficiency. So that kind of gives you an idea on what that looks like. Now, what I'll do here is I will show you a couple videos of the actual rack on the surface. So this will show you how it comes up to the surface. They can visually inspect the membranes from the surface. They can hose them off, make sure there's no biofilms or anything like that developing on the surface of the membrane. Then they can drop those right back down into the tank and go back into service. If they have to pull them for replacement issues, this is what that looks like. They can walk that right across that gangplank. You can see the banana style mixers here on those piers. And you can see the racks down below. This is sufficient to give enough dissolved oxygen to that entire basin. So you can, it's get a little stuck here. I apologize for that. It's refreshing. All right, that's gonna not cooperate with me, but you get the point there. Again, so this is what I'm talking about with, you can see this picture here with fine bubble grids, the amount of diffusers. Now, Jaeger can supply diffusers and they have some really unique designs, but the really key thing for helping these operators, again, with these challenges of maintenance, manpower, and energy usage, are some of these, retrievable designs that we're talking about. If you guys have any questions, feel free to interrupt, but we'll keep right on rolling if not. Okay. So you can imagine how happy an operator would be if we could, you can come in and tell them, sorry about that. I thought we got disconnected. You guys can see my Kate. Can you see my screen okay?
Yep, you're good.
Okay, good. So that kind of highlights, like I said, you can imagine how happy an operator could be if you could tell him you don't have to do anything inside your tank, which is the biggest tank system typically. Rebecca's asking a question there. Kate, did you catch her question real quick?
Oh, sorry. She asked, do you notice any differences between rectangular and circular tanks with these diffusers?
No, they're not limited by tank geometry. So we can work, as you saw there in maybe a couple of the pictures, we can put these things in long rectangular tanks. We can put them in circular tanks. We can put them in oxidation ditches. Let me go back real quick and I'll show you a quick video here on the oxidation ditch side that might be beneficial to kind of give you a little bit more insight into that, Rebecca. So this one right here. So this is an oxidation ditch retrofit. What we did is we put the aeration on one side of the chase, and then a grid over here where you can see the operator has the ability to walk right out over one of the channels and go to the operational side. So then we have a series of mixers in here that are pushing flow through the system, but these are also on retrievable grids. So you can retrofit an oxidation ditch even in this particular type of a design. So yeah, the tank geometry usually doesn't matter. Back over here. All right. So when we talk about aeration, what you typically will see is there's a mixing component to aeration along with the aeration energy itself for dissolved oxygen transfer. Normally, those things will drive up energy usage. So if you can find a way to help the operator decouple his mixing energy from his aeration energy, that can also have a big influence on how big that aeration system is and how much horsepower you're pushing in there. Significant energy savings. So like I said, aeration can be energy intensive, especially when those two things are coupled together. Aeration, fine bubble diffusers, because just inherently by design, they're up off the bottom of the floor. They could be a foot off the floor, which means you could potentially get solids deposition inside that tank. And it could be ineffective mixing, and you also potentially could have to deal with below water maintenance if you have mixers in there that you have that are rotating mechanical mixers. So one of the lines we work with is it's a large bubble mixing system by a company called Pulsair. You guys maybe have seen some of these types of technologies. These diffusers, which you see here, we call them accumulator plates they sit right on the floor. And then they are programmed to pulse large amounts of energy in large bubbles into those aeration basins and tanks, and effectively mix every corner and every surface of that tank right at the bottom of the tank. So your aeration grid would sit up above these, and then these would be strategically placed within that structure, and then that acts as your mixing mechanism. And there's a huge energy reduction component to that, and it completely eliminates solids deposition. So you couple this together with the aeration design, there should never be an instance where you have to get into that tank to do maintenance or clean anything out of there. Which obviously is a big deal for the operator. And that is all stainless construction, really easy to deploy and easy to design. And again, big impact for the operator. Then our last topic of discussion here is biosolids management. And obviously, this is going to become a more prevalent issue for operators, especially when we're talking about contaminants of emerging concern, such as PFAS and PFOA. We've got projects we've worked with where we've helped wastewater treatment plants deal with impacted biosolids, specifically when dealing with PFAS and PFOA. So when you look at the challenges associated with biosolids management, one of the big ones is obviously changing regulations. There's more and more pressure now on land space. Operators are having the challenge of having to deal with limited land space, land being taken away, and it being more costly to rent the land or pay to be able to apply the biosolids to the land. That such as landfilling and land applying restrictions. That's going to become more and more prevalent as we start to see more of these contamination issues in communities backing up and farmers backing up saying, I want you testing, and if there's stuff in that material, I'm going to start to limit you or completely eliminate your options for dealing with your biosolids. Because when you look at, for instance, in Wisconsin, a lot of biosolids are liquid land applied or cake land applied to farm fields. Because we got a lot of wide spaces and things like that. But we see that challenge becoming more and more prevalent with these operators having to figure out, what am I going to do? The other thing that is the climate too. When you're going out and land applying, they have to land apply in the spring and the fall. If they run into weather concerns, they end up with a capacity issue, and all of a sudden you've got a problem because you're running out of storage capacity because you can't get out on the land to be able to apply it to the farmlands. That all obviously drives up cost as landfills start to restrict, land starts to get limited, the cost per acre starts to go up, and it becomes an operational challenge and an OpEx challenge. So you ask yourself, all right, what can we do to help those operators solve that problem? So one of the technologies that a lot of people use are dewatering presses. So you've got typical belt presses, screw presses, centrifuges, rotary presses, things like that. Those things can be highly maintenance intensive. They can use a lot of water, they can use a lot of energy, and they can be physically large in footprint. What you're seeing here in the picture on the right is our PW Tech Volute dewatering press. That particular press is one of our projects we installed up at the city of Marinette, and we are processing 21,000 gallons a day at roughly 2.5% feed solids through that unit. It only uses, its footprint overall is about 12 feet long by 6 feet wide. And we only use about 5 horsepower total and about 20 to 40 gallons per hour of wash water. It's fully self-contained and fully automated. So when these guys come in, they hit the start button and they walk away, and that thing processes. They'll let it run 5 days a week, 24 hours a day, fully automated. So again, we're helping them reduce their energy consumption. Their maintenance is extremely simple on this, and they don't have a lot of manpower where they have to babysit the system. This particular technology, if you look at the other picture here on the left, it's got 2 screws on it. We can put up to 6 screws on a skid, excuse me, which basically gives you built-in redundancy. So you can run 24 hours a day and you don't have the fear of something mechanically breaking down and all of a sudden you can't process your sludge. What that allows you to do is make the system physically smaller too. So that has a big impact for them. Only maintenance they have to do on this thing is once every 15,000 hours, this upper assembly comes out on a rail. It's a cartridge. It takes 4 hours to rebuild the press. Again, going to that same messaging we're trying to kind of talk to you guys here about today. Can we do more with the existing infrastructure and help them reduce these manpower and maintenance requirements and cost requirements from an energy usage standpoint? So then what they do here at this facility, because they have a PFAS problem, the cake discharges at roughly 22 to 23% into a cake pump. And then we take that over to a biosolids dryer, which is sitting right here. All of this equipment was put into a footprint that was 15 feet wide by 55 feet long into an existing building. So this goes to, they came to us with a challenge. They said, we have to fit it in this existing room. If we can't get in the existing room, the cost of the project is going to be too expensive because we're going to have to start knocking down walls, doing a big civil infrastructure project, and we met the challenge. We were able to engineer this and put it in an existing building. So what this dryer is it's a dehumidification system, and if you look at the picture on the right, we're taking that cake and then drying it to 93%, which then gives them the ability to manage the volume of solids because it is impacted because they only have one outlet and they have to take it to a landfill literally that's out in the state of Oregon, believe it or not. So they have to put this stuff on rail cars and it's got to be trained to Chicago and then out to the West Coast. They had to get their volume down because it would cost them a fortune if they were lugging around water in either cake form or liquid form, obviously. So this thing was, this technology was able to reduce the volume of sludge by 60 to 80%. Again, 90+% dry solids, significantly efficient from an energy standpoint. So low OpEx cost. It also gave them the ability to control their outlet of their biosolids. So let's remove the PFAS and PFOA contamination issue from this. A municipality would be able to now finally not be at the mercy of land spreading during certain times of the year where there's weather problems, changing land requirements, things like that. They have complete control over that, and they have a huge volumetric reduction. Technology doesn't this is fully automated. So the entire biosolids process is fully automated where they come in and they run it for 5 days a week, 24 hours a day, as I stated earlier. They turn it on Monday morning and they shut it off on Friday afternoon. They'll occasionally walk by once or twice a day, just check what's going on. They have security cameras on it so they can keep an eye on it from their phones. And this did not significantly increase the requirements of the plant from a manpower on a daily basis standpoint. I mean, obviously it increased some maintenance stuff where they got to, change filters and things like that. But in comparison to what they could have put in there, it's a significant advantage. So again, huge impact for the operator, solved the problem, but yet was very cost effective in doing so. And it didn't create additional challenges for the operator. So kind of to sum up here, where we talk about what we, our obviously our message to here today to you was, can we look for technology solutions to help aging wastewater treatment plant operators continue to meet their required regulations without breaking the bank on it, without overstepping the amount of manpower they have and creating more complexities in their operation? Can we help them improve plant capacity by simply adding technology instead of having these major expansion projects? Assisting them in adjusting influent challenges and effluent regulations. And again, like I said, can we upgrade without having to do a whole plant upgrade? And setting these systems up also so they can be as automated as possible so we keep that amount of manpower increase down to a minimum for the operators so they can effectively still do their job, again, doing more with less requirements that get put on them. So hopefully you got something out of this here, and it looks like I got us done here right at the 1 o'clock hour. So